Okay, so in this particular slide, what we have observed that it's similar picture what we have seen previously, and let's calculate the energy for that. So let's begin with the zero position. Then on the either side of the zero position of the mono dimensional crystal or a one dimensional crystal at R0, as it is shown by the red arrows line, uh, I am finding a chlorine ion, and therefore it is a uh, attractive in nature, because sodium is a positive ion, chlorine is a negative ion, and therefore they are attractive in nature. So if I will calculate their Coulombian energy or the attractive Coulomb energy, it would be preceded by definitely with the negative sign. uh, the factor 2 is because of two chlorine ions are in either side of the zeroth position sodium ion, and therefore I am multiplying this factor with a 2. And another point of important thing is the r0 distance. As the lattice distance is r0 or equilibrium distance is r0 for this particular bond, if I will go with the further distance, then it would be a twice of R0, but I am finding the identical ion, that is a sodium ion, on the left again as well as on the right. And it is very common in case of a crystal, whatever you are finding at a one particular distance, you must find the similar kind of the ion or a metal or a material on the other side, and that is what the periodic repetition. So here at a twice of r0 distance, you are finding again a sodium ions on either side, and therefore they are like charges and therefore repulsive. So now in the second step of the Coulomb energy calculation, I am finding a sign is positive because they are repulsive energy. Again, the 2 factor is because of a 2 sodium ions on either side of the zeroth position sodium ion of my single axis or the one axis. And here the distance is not similar what you have seen in the first step, but it is the distance is increased by a 1 unit of r0, and therefore it becomes twice of r0, and so on for the further part of the axis. You can calculate it. Now if I look at this particular series, what I am observing, this perfect that is the e square upon 4 pi epsilon 0 r0, I can take it as a common. Then the series will be rewritten as with the square bracket, and it would be represented in similar identical uh, power series like log of 1 plus x is equal to x plus 1 half x square plus 1 third of x cube minus 1 4 of x power to the power 4. And if you look at here, the all even number are with the negative sign and all odd number are with the positive sign. Let compare with this square bracket, then the x is equal to 1, and therefore the following relation can be rewritten as in terms of log of series, and that would be e square upon 4 pi epsilon 0 r0 in a square bracket twice of log of 1 plus 1, as x is equal to 1 in the present case. And therefore, as it is given in the equation number 3.17, e square upon 4 pi epsilon 0 r0 in a square bracket of twice of log 2. So here the underlined twice of log of 2 is nothing but the Madelung constant of a one dimensional sodium chloride ionic crystal. So if in exam someone asks you that calculate the Madelung constant for a one dimensional crystal, then your discussion would be up to this equation number 3.17 only. But in general, the question would be shaped as calculate the one dimensional Madelung constant as well as the enhance this model for the three-dimensional crystal as well. In that scenario, we need to calculate, or we need to extrapolate our one-dimensional model for the three-dimensional model, and there would be in the shape of something like this. Let us again remember or sharpen up our main points. Then twice of log of 2 is nothing but the Madelung constant per molecule of a ionic solid, because right now we are just calculating a one bond on either side of the 0th position of a sodium atom. But in general, if I will say that this is a 1 kilomole of monodimensional or a unidimensional or a single dimensional crystal, then there would be a Na number of the atoms do available, or the equivalent number of atoms, that is nothing but the Avogadro number, and therefore that constant should multiply by Avogadro number. So the Madelung constant per kilomole would be twice of Na log of 2. This is only for one dimensional crystal. Let us enhance and extrapolate this model for a three-dimensional crystal. As you can see in the figure number 3.6, that is a NaCl structure. I think you all guys are certainly come across with the same structure in your 12th standard or maybe in 11th standard. If you look at as a core part of your crystal, that is a position A, and solid colored atom is nothing but the sodium ion, and the hollow circle is representing the chlorine ion. So let us try to speculate the model, calculate the model for a Madelung constant for a three-dimensional model. Then here I would be underline the process, and that is, let us calculate how many number of the ions are at an identical distance. Then from the position A, this distance is basically a R0 distance or a equilibrium distance. So at a R0 distance, I am finding in all 6 number of chlorine ions, and therefore the equation or the first step of the equation where the multiplicand factor is 6. Naturally the distance is R0, so what we have seen in the one-dimensional crystal, it is repeating here again. Let us see in the structure where these 6 ions are available. So I have made an animation for you guys. I think you will able to see now with the colored red dot on the position R0. So this is 1, this is again at a R0 distance. The second atom is over here, this is again at a R0. The one is in the backside of the A, that is also at a R0, and one is on the right hand side, one is on left hand side, one is front of the A, one is back of the A, so that is 4 atoms of a chlorine, one at the bottom of the A, that is again at a R0, and one at the top of this. So in all there is a 6 chlorine ions are with the same distance at R0, and therefore the very first step is multiply by with the 6 e square upon 4 pi epsilon 0 R0. I think everybody knows epsilon 0 is a permittivity constant of a free space. Let us check it up the another distance and how many number of the ions are available over there, as shown over here by the blue arrow, and that is a diagonal distance in a one plane. I am repeating, blue arrow is a diagonal distance in a one plane. So as I mentioned over there is a 12 number of such positions are available. Let us calculate where these 12 positions are available, and if you look at in the equation, then this all 12 positions are at a twice of under root of 2 R0 distance. and it is very understandable because its diagonal is a applying with the Pythagoras law. So both the adjoining points are with the distance r0, and the vertical distance is also r0. So diagonal distance according to the Pythagoras law, it become under root of 2 r0. And as I am mentioning, there is a 12 such positions are available. Therefore the equation 12, I mean equation multiplicand factor you are finding in the second step, that is a 12. And here let us calculate where are this. So blue dot are representing the sodium ion, so the position A ion is also sodium. Now we are calculating another 12 position with the sodium ion at a distance under root of 2 r0. So let us check that. So in this plane I have a 1, 2, 3 and 4. So if you look at here, this is a one plane through which passing through the atom A in a vertical fashion, and that is at a distance root 2 r0. If I take the another plane at a horizontal to the present discussion plane, then I do have another 4 position, number 1, number 2, number 3, number 4. So this is 4 plus 4, 8 sodium atoms are at a distance of under root 2 0, but still there is a one more plane is with the same one which is orthogonal to this both plane, and that would be this one, 1, 2, 3 and 4. So in nutshell, there is a 12 dots of blue are there, and therefore there is a 12 sodium ions are at the same position, that is of under root 2 r0, and therefore the second step in the total energy calculation, and that is with the 12 e square upon 4 pi epsilon under root 2 r0. And the last step what we have seen in the sequence of the Colombian potential energy, and that is again with the negative sign. Negative sign, that means a attractive energy, and that means now next candidate must be chlorine. And if you do remember the previous slide, there is a periodic repetition of a sodium chlorine, sodium chlorine. So naturally one step with the negative sign, second step with the positive sign, next step will be the negative sign. As it is mentioned in the equation, it is a 8 number. So here it is shown in the figure 3.6. I am showing with the yellow arrow, and that yellow arrow is basically a body diagonal, and if I will check it up the body diagonal length, it would be root 3 r0. Root 3 r0 is a body diagonal of one of the corner of your entire cube, and therefore if such position, if I am going to calculate from the A, then the top plane of the position A as well as the bottom plane and their corner, so in all there would be a 8. So equation sequence having a 8 such position at a equal distance at a identical distance, that is root 3 r0. Let us check it up with the yellow dot. This is again the animated part. You just have a very clear understanding where this 8 positions are lying. So number 1, number 2, number 3 and number 4, and these 4 positions are on the top plane of the position A, and same way you have the another 4 ion position at the bottom of the position A. So that is 1, 2, 3 and 4. So in all there would be the 8 yellow dots, and therefore the third factor or the third step of the potential energy calculation, that is 8 e square 4 pi epsilon 0 under root 3 r0. Now this kind of the sequence of this particular potential energy will be continuing. So my basic logic says that the next position will be attractive or repulsive. So I can understand one factor is a negative, the next chain sequence will be positive, the third is negative, then fourth must be positive. So the sign is correct, what you have speculated, that is positive. And what will be the number of electron and what will be the distance? Can anybody guess? Yes, so maybe few of you have having an idea that this is a unit crystal, and you can assume a next adjoining entire such crystals will be available. One crystal on your right, one crystal on your left, one crystal in your front, one crystal on your back, one is on top and one is at the bottom. So that way you having a 6 another such kind of a crystals are making a cage around this particular my present crystal, that is given in the figure 3.6, and therefore the distance become twice of R0, but the number of available ions are again same, that is a 6. And same way you can check it up with the next to next to will be again 12, 8 are following, but only the denominator distance will be increasingly and therefore the equations will be changing. Let us visualize the entire equation again. So 12 number of sodium ions at a distance of under root twice of R0, and 6 number of sodium ions at a twice of R0 distance, and therefore they are finding in the equation similarly. And here you can take the common factor as a e square upon 4 pi epsilon 0 R0. So in a square bracket you are finding the rest numerical numbers, and this is would be only for a one molecule or a one bond in a three-dimensional setup. But in general, when I am going to take a crystal, there would be a many number of crystallites will be there. So in general it is always measured by weight. So let us take 1 kilomole crystals. That means there would be available number of atoms is very predefined, and that is a multiply by Avogadro number. So I am here multiplying with the Na. So Na e square upon 4 pi epsilon 0 R0, and the same square bracket, that is representing the Avogadro number, and the square bracket is nothing but our Madelung constant. In general, book has mentioned with the character A. So U is equal to minus Na e square capital A upon 4 pi epsilon 0 R0, where A is nothing but your Madelung constant. Now it is also depend on the person who is taking care of the square or curly square bracket, that up to what extent he want to continue the series, and according to that he has to calculate, maybe up to 10th position, maybe up to 12th position, maybe up to 20th position, and there you have to truncate the sequence, and that would be representing a number. So in general 10 to 12 numbers are considered to be a very good better speculating result, and for that crystal Madelung constant is calculated 1.75. There are other few examples are given, like cesium chloride and zinc blend. Do you know what it mean by zinc blend? It is nothing but the zinc oxide or the ZNO, and I am pretty sure that many of you are knowing that ZNO is the prominent candidate for the solar cell, or today's renewable energy, or one of the prominent area where you can develop your career as a part of research, and that is a solar cell or the solar renewable energy, where the solar cell to be understood, and that is nothing but the zinc blend. Thank you so much. Stay home, stay healthy, stay safe, and the next series will be continuing. Okay, and one more information I would like to share with you. This would be the end of the your syllabus segment A. As I told you in beginning, the PH 3501 unit 1 is divided into 3 category: category A, category B, and category C. So category E with this is almost about to finish. only two topics are there, but it is very elementary and you had already studied in your 11th and 12th standard study. So on this online sessions I am not going to discuss again and again, but yes, still I would be like to tell you that please refer the book, refer the material, and prepare the ionic crystal property, covalent crystal property, and the metallic crystal property. So many time it is also asked as a short note questions, like discuss the five property of each crystals and where you are about to crystal. Now this is a higher education, so naturally when you are mentioning a property you have to also discuss the reason or the scientific reason as well, right? So again, stay home, stay safe. Thank you so much.